Welcome back. This lecture is going to cover electromagnetic waves, planetary energy balance, temperature, and we're going to end by solving Earth's energy balance in order to estimate its temperature. So let's get started. The first thing we have to cover is the electromagnetic spectrum, which is visualized here. That is because all of the energy from the sun comes to Earth as electromagnetic waves. Solar radiation includes visible light, that's why we can see it, but it also includes gamma rays, X-rays, ultraviolet rays, sometimes called UV radiation, infrared radiation, and radio waves. Electromagnetic waves are oscillating magnetic and electric fields that propagate in space and time and transfer energy, just like ocean or sound waves. But EM waves are different in that they can travel in a vacuum, that is to say, the vacuum of space. Wave characteristics are visualized on the right. The crest is the high point or peak, and the trough is the low point. The wavelength is the distance from crest to crest, or trough to trough. The period is the time between the passage of two successive crests, and the frequency is how many oscillations happen per second. Let's go over the relationship between a wave's frequency, period, and wavelength. The speed of propagation of light, and all EM waves, also known as c, in a vacuum, is a physical constant, about 300,000 kilometers per second. That's the maximum possible speed in nature. The frequency and period and wavelength are all related as follows. The speed of light equals the frequency of a wave times the wavelength, which is equal to the wavelength divided by the time period. This tells us that the frequency is also equal to 1 divided by the time period, something we already knew based on the definitions of frequency and period we went over in the previous slide. What this means is that as frequency increases, the wavelength decreases. The opposite is also true, meaning that lower frequencies are associated with higher wavelengths, and vice versa. Here is our electromagnetic spectrum again. That squiggly line is showing the wavelengths for all visible light. The numbers on the x-axis are also stating the wavelengths. The upper x-axis is showing the wavelengths for all EM radiation, while the lower x-axis is just showing wavelengths for visible light. Looking at the squiggly line, which is visibly showing wavelength, we can see that shorter wavelengths, measured from crest to crest, have higher frequencies, since all EM waves travel at the same speed. Said another way, because all EM waves travel at the same speed, shorter wavelengths must have a higher frequency, and longer wavelengths must have a lower frequency. EM radiation with higher frequencies, like UV rays, X-rays, and gamma rays, cause DNA damage. This is why we don't hang out in nuclear reactors, don't get X-rays or CT scans for fun, and it's why we wear sunscreen. So let's talk about the EM radiation produced by our star, the sun. The process of nuclear fusion, because the sun fuses hydrogen into helium, produces huge amounts of energy in the sun. This makes it very hot, so it produces a lot of EM waves. The surface temperature of the sun is about 5,702 Kelvin. This determines its color and the total amount of energy it emits. EM radiation is actually emitted by all objects, and the EM waves emitted depend on an object's temperature. The hotter the body, the more energy it emits. Also, the hotter the body, the shorter the wavelength of peak emission. The Stefan-Boltzmann law of idealized blackbody emission determines how much energy is emitted according to temperature. It says that the energy emitted equals some constant, which we're not going to learn for this course, times temperature raised to the 4th degree. Notice that temperature is raised to the power of 4. It is rare in nature to have such a strong dependency. While not all EM radiation is visible light, for visible light, the color that is emitted changes according to temperature. This determines the color of stars. The temperature on this graph is on the x-axis, and it is measured in Kelvin. We are more used to thinking of temperature in degrees Celsius or Fahrenheit. Kelvin is an absolute temperature scale for scientists, and you can convert between degrees C and Kelvin by adding about 273 to a temperature that's reported in Celsius. Back to color. Hotter objects glow more blue, shown on the right, while colder objects glow more red. Obviously, these are all stars and much hotter than the temperatures we are accustomed to, but you can see there's a fairly wide variation in star temperatures out there. Really hot stars emit substantially more amounts of UV radiation than our sun. There are lots of different types of stars that range in size, heat, and lifetime. Most stars are currently classified under the Morgan-Keenan or MK system, shown on the x-axis to the right, ranging from O-type, which are the hottest, down to M-type stars, which are the coldest. Note that the letters are not sequential. On this diagram, hot and bright stars are in the upper left-hand corner, and cool and dim stars are in the lower right-hand corner. You can see there are some cool but bright stars, termed giants, and some hot but dim stars, termed white dwarfs. Most of the stars, including our Sun, follow the main line. Our Sun is a G-type star, and you can see it in there. As a star gets bigger, denser, and hotter at the center, the rates of fusion rise much faster, and the star loses energy more quickly, so they tend to burn out faster. That means they have a shorter lifetime. Ultimately, the amount of EM radiation, or irradiance, that nearby objects receive will depend on the type of star. One of the conditions that decreases habitability is too much UV radiation on a planet. UV light can cause mutations and kill cells. That is why we wear sunscreen, to protect us from skin burns. Ironically, mutations are also key for evolution. UV light also helps us because it allows us to make vitamin D, which is a necessary vitamin. The ozone layer currently protects life on Earth's surface from too much UV light. This is another key habitability factor for Earth's modern life. The formation of the ozone layer allowed for the evolution of terrestrial organisms on Earth. Remember that EM radiation is actually emitted by all objects, and the EM waves emitted depend on the object's temperature. The hotter the body, the more energy it emits. That means that both the Sun and the Earth produce a range of EM radiation, just of different wavelengths. The Sun emits a lot more energy per unit area than the Earth does. The Sun emits shorter wavelengths, aka shortwave radiation, some of which is visible, which is why it visibly glows. The Earth emits longer wavelengths, also known as long-wave radiation. These are invisible infrared waves, which humans cannot see. That means that Earth is visible due to solar light, not because of Earth's own infrared glow. Note, the surface temperature of the Sun has been rounded up a little here, but we can visualize objects that emit infrared radiation with infrared cameras. Infrared cameras have many applications, such as fever detection, firefighting, and so on. In this lecture, we're going to show how to determine the Earth's temperature, as viewed from space, using the amount of infrared light it is emitting. So let's start with that. First off, you have to know that the Earth receives shortwave radiation from the Sun. That's because the Sun emits shortwave radiation. When it reaches the Earth, some of it is reflected back to space by clouds, while some is absorbed by the atmosphere, and some is absorbed at the Earth's surface. The Earth emits long-wave radiation, according to the Stefan-Boltzmann equation. The radiation it receives is transformed because it is colder than the Sun. The energy has to be balanced, meaning that what Earth receives is re-emitted, and that's because Earth has a stable temperature and climate. On this slide, we're going to discuss the average annual incoming solar radiation over the entire globe. First, you need to understand the circle of illumination. At any moment, half of the Earth's surface is lit by the Sun, and the other half is in darkness. The Earth intercepts as much energy from the Sun as a flat disk of the same radius, so even though the Earth is a globe, only half of it is lit. The average annual incoming solar radiation is 1,360 watts per meter squared. The area of a flat disk is pi r squared, and the area of a sphere is 4 pi r squared. So Earth receives the total amount of incoming solar radiation multiplied by the area of a flat disk divided by the area of a sphere, or 1,360 watts per meter squared times pi r squared divided by 4 pi r squared, which equals 1,360 watts per meter squared divided by 4, or 340 watts per meter squared. Note that we are approximating the numbers a little bit, so they're slightly less than the image that is shown to the right, but the image on the right is a really good visual. An important point to remember is that not all incoming solar radiation is absorbed by the Earth. Some of it is reflected back to space. Albedo is an expression of the ability of surfaces to reflect sunlight, thereby not getting heated by it. Light-colored surfaces return a large part of the sun's rays back to the atmosphere because they have a high albedo. Snow, which is pictured, and clouds, which are not pictured, both have high albedos. Dark surfaces absorb the rays from the sun because they have a low albedo. The ocean has a fairly low albedo, though this varies quite a bit. Forests have a low albedo, and asphalt has an extremely low albedo. All of these factors affect the planetary energy balance for Earth. The amount of energy that the Earth absorbs will be the solar power falling on Earth times 1 minus Earth's albedo. Remember that albedo equals the fraction of radiant energy reflected off a planet. This reflected energy does not warm the planet and does not participate in forming its climate. But the Earth will re-emit the energy that it absorbs. This is because inputs have to equal outputs for long-term stability. Put another way, incoming solar radiation times the fraction absorbed will equal outgoing emitted radiation from Earth. We already know that outgoing energy for Earth will be the Stefan-Boltzmann's constant times temperature raised to the fourth power. So let's solve the energy balance for Earth to estimate the temperature of Earth. Recall from a few slides ago that the Earth receives 1,360 watts per meter squared divided by 4, or 340 watts per meter squared, from the Sun. Then we have to multiply that by 1 minus the albedo of the Earth. The average albedo for Earth is about 30, so that term will be 1 minus 0.3. That will equal the Stefan-Boltzmann constant times Earth's temperature raised to the power of 4. If we plug all these terms in and solve it, we get an absolute temperature for Earth of 255 Kelvin. Let's put that in perspective. Solving the energy balance equation for Earth yields a temperature of 255 Kelvin, or negative 18 degrees Celsius. That is a lot colder than the actual averaged surface temperature of Earth, which is 288 Kelvin, or 15 degrees Celsius. Earth's temperature, as seen from space, is negative 18 degrees Celsius, but that is not Earth's surface temperature due to the presence of the atmosphere and its greenhouse effect. Greenhouse gases let short-wave radiation through and absorb long-wave radiation and re-emit it, with some going back to Earth to reheat it and the lower atmosphere. The greenhouse effect is a natural process provided by the atmosphere and keeps the planet warm and habitable. The atmosphere is a key planetary habitability factor in this and other ways. We can calculate the strength of the greenhouse effect by calculating the difference between the energy balance temperature we derived and the actual temperature of Earth. The strength of the greenhouse effect on Earth is about 33 degrees Celsius, or 33 Kelvin since we are only calculating a difference here. That means that greenhouse gases are keeping the Earth 33 degrees warmer than it otherwise would be. Greenhouse gases are actually keeping the Earth habitable. However, while the greenhouse effect keeps the Earth habitable, more greenhouse gases mean more warming. Humans are currently putting massive quantities of greenhouse gases in the atmosphere and causing increased warming due to the greenhouse effect. And this is a problem that we will revisit throughout this course. That concludes the material for this lecture. Let's go through and review the main points. Electromagnetic waves come in a range of frequencies. An EM wave, like any wave, has elements such as wavelength, crest, trough, period, and so on. All EM waves travel at the speed of light in a vacuum. The Stefan-Boltzmann law describes the amount of emitted energy from a body based on temperature. The Sun emits shortwave radiation, some of which is visible. The Earth emits invisible long-wave radiation, which is infrared radiation. The Earth's energy balance equation is based on the principle that the energy received must equal the energy emitted, allowing Earth to have a stable temperature and climate. Earth's energy balance equation solves for a temperature 33 Kelvin lower than the actual average surface temperature because the energy balance equation does not factor in the greenhouse effect. Thanks for sitting through the lecture. To test your learning, I suggest you review the material and make sure you can answer these questions.